Today we're going to talk about these two subjects right here, potential energy and conservation of energy. So let's have a quick look at what we did last class. We did work, right, due to a constant force. That's something we've been doing recently. It's a dot product between the force vector and a displacement vector, and when you do the calculation, it's F times D times the cosine of the angle between them. There's also the work due to a varying force. So this is general. Here, the work due to a varying force. If you have any force that changes with position, you integrate it from the initial position to the final position to get the work done. And we use that to calculate the work done for a specific case of a spring. If you remember, the force due to a spring is minus kx. And when we did that integral, we saw that the work done was 1/2 kx initial squared minus 1/2 kx final squared. And of course, this was related to 1/2 mv squared. We are missing one equation here, which I will add here real quick. It's the work kinetic energy theorem. The work kinetic energy theorem, which basically says that the work done is equal to the change in kinetic energy. So those are the key ones. We also looked briefly at the power, which is sort of a rate at which energy or work or whatever is used up over time, and that has units of watts. We won't be using that today. I just wanted to mention it to remind you. So when you throw a tomato up, gravity does net work on it that is negative, right? The potato, what is this? A tomato. When the tomato is traveling upwards, gravity is doing, as it's traveling upwards, gravity is doing work downwards. So this would be the force of gravity while its displacement is upwards, so it's negative work. And when it's falling back down, gravity does positive work. And that's what's interesting about this kind of situation, is that gravity does negative work, taking kinetic energy as it travels up, but then it gets that kinetic energy back as it's moving back down. Gravity does positive work, increasing its kinetic energy. So we're going to describe this kind of situation where the energy can be taken out, stored, and then returned as the energy being stored as potential energy in the tomato earth system. So we're going to treat a system as something that includes something like the tomato and the earth, and that the energy is stored between those two things. Not all energy removed via work can be returned to the object in this matter. So an excellent example of this is friction, right? If I have a box traveling to the right, friction takes energy out of it, and you can't return that back to the kinetic energy of you can't return that back. That energy taken out of the box as it's slowing down, as it slides along the path, is lost to heating up the floor or making sound. Situations like gravity, where the energy can be returned, we call those conservative forces. Forces where the energy can be removed and returned. It's in certain situations. Situations like friction, where the energy cannot be returned, is called a non-conservative force. So we're going to look at conservative and non-conservative forces. So when only conservative forces are acting on a particle, it's a much simpler problem. It's really, really helpful. We're going to study conservative forces and how they affect energy. So the net work done by a conservative force on a particle moving around a closed path is 0. So if I start, let's say, here at A, and I go around a path and I come back to here, the total work done by a conservative force is 0. Another way to think about it is that the work done by a conservative force on a particle moving between 2 points does not depend on the path taken by the particle. So if I start at A here and I travel to B, either via path 1 or via path 2, the amount of work done is the same in either case. Okay, so for those types of forces, we can use potential energy. Mathematically, that means that the work from A to B via path 1 is equal to the work from A to B via path 2. So here's an example here. If I have is that a block of cheese? I guess a block of cheese at the top of a hill. If it follows down this path, up, back down, and over to B, the work done by gravity as it goes from A to B will be the same as if we just move it sideways where no work is done and then move it straight down. Okay, so that's the type of situation that we're going to use. So we're going to define the change in potential energy, that energy stored in a system, as the negative of the work done. So delta U is going to be our symbol for expressing potential energy. Is going to be equal to minus the work done. So for gravity, we show that if you do an integral of the force, or you just do force dot force dot displacement, the work done by gravity is mgy initial minus mgy final, which if I factor out a -1, then I factor out the mg, this becomes the y final minus y initial is delta y. So the work done by gravity, if you move from an initial to a final position, is mg delta y. So that means that our potential energy is just going to, or change in potential energy gravitationally. So we want to mention that this is change in potential energy for gravitationally is going to be mg delta y. Okay, so that's the gravitational potential energy associated with a particle depends only on its vertical position. It doesn't matter on the left-right motion. It only depends on its vertical position. If we pick a spot to be 0, so let's say this is the ground, and I pick here to be y equals 0, right, then the potential energy of this, I guess it's a heart for some reason, up here, that is 10 meters up. And this heart is, I don't know, it's very heavy. It's a gorilla heart, something big, is 2, then the potential energy of this particular situation here will just be mg times y, and that's relative to its height at that point. So we put in 2 kilograms times 9.8 meters per second squared times y, which is 10 meters, and 2 times 9.8 is 19.6 times 10 is 196, and a kilogram meter per second square is a newton, and a meter times a meter makes it a joule. So that's the potential energy of this apple, or this, sorry, what is it, a heart at this point. So that's potential energy for a heart at a certain location. Another example here, if I have a building here, so here's my building, right, and when I first jump off the top of the building, why not, and let's assume that I am happy because I'm pretty sure I'm going to survive. All right, so I jump off the top of the building, and the building has a height of here 100 meters. So that's y at the top. What's my potential energy at the top? What's my potential energy when I am only 20 meters up? And let's say that my my mass here, I don't know, 80 kilograms. Okay, so, and this is going to be here, and down here is going to be y2. So we can calculate all that. We can calculate the potential energy at 1. It's going to be the mass times gravity times y1. So 80 kilograms times 9.8 meters per second squared times the height of 100 meters at the initial position. That's all going to work out to joules. And just for fun, I'm going to pull out the calculator here. Okay, so 80 times 9.8 times 100. So that works out to about 78,400 joules, right? And if I were to do the same thing for y2, mg y2, that's just going to be, instead of times 100, it'll be times 20, and that gives me an answer of 15,680 joules. Nice, simple example. A 2 kilogram book is dropped as shown. If you take y equals 0 to be at the ground, we usually take y equals 0 to be in the ground. Sometimes you want to choose y equals 0 to be somewhere else, and that's okay. We're going to learn a little bit about that later on, that you can choose y equals 0 wherever you want, but for the most part, we'll take it to be on the ground. Take y equals 0 to be on the ground. What is the initial potential energy? What is potential energy at little d? So that's down here when the kid catches it. And what is the change in potential energy? So we'll just write down how you go about calculating it. I think it's very simple. So what is the initial potential energy? So the initial potential energy will be mgd, where m is 2 kilograms here. G is 9.8. B, the potential energy at D, which I'll call U final, is going to be mg little d. And then the change in potential energy will be U final minus U initial, right? So it'll be, if you do mg little d minus mg big D, so just mg d minus d. If we plug in the numbers for that, what do we get? I say, let me get there it is. So let's plug it. So m is 2 times 9.8 times, and then 1.5 minus 10. So we get minus 166.6, we'll say approximately minus 167 joules. So that box that got dropped from the third story lost 167 joules of energy as it went down. And we're going to learn later on that that 167 joules that it lost was gained as kinetic energy. Here's another basic example. We're just going to do this in terms of letters. Find the change in potential energy from the first hill to point A. Well, as we said, the only thing that matters for the potential energy is the height above the ground. So, the change in potential energy for point A is going to be mg height at point A minus the potential energy at the beginning, right? Which was also height. So it started on the first hill, it started at height h, and it ends up at A at the same height, so it doesn't matter. So that means that the change of potential energy is 0. For this set for point B, right? How high is point B? Well, it's at h over 2, so it's going to be mg h over 2 minus the initial height, which is mg h. So that ends up being minus mg h over 2. So that's the change in potential energy from the first hill to B. So now let's find the change in potential energy from the first hill to C. Well, C, the height is 0 here. You can see that y is equal to 0. So it's going to be mg 0 minus the initial, which is the first hill, mgh. So it's just minus mgh. Right, so the change in potential energy from the first hill to A, B, and C, it increases as the difference in the height increases. So how would this change? By the way, well, if I were to double the mass, what would happen? Well, if I doubled the mass, then I would double all the answers, right? Because m would be times 2. So each answer would be times 2. And in this example here, I believe from the textbook, what is the change in potential energy when this ice flake is at the bottom of the bowl? So if I release that ice flake, it has a certain mass, 2 grams, and it's sliding down a bowl that's a height that has a radius of 22 centimeters. So that means that the delta y from the ice flake is 22 centimeters, right? 22.0 centimeters. So that means it's pretty easy to calculate the change in potential energy. So the change in potential energy is going to be mg y final minus mg y initial, or just mg delta y. And we said delta y is delta y in this case is 22 centimeters. So m is 2 grams, so 0.0020 kilograms, right? Times 9.8 meters per second squared, times the distance it went down. So it went down 22 centimeters, so 0.220 meters. So if I had to calculate that, which I believe I do, let's calculate that change. So 0.002 times 9.8 times 0.22, you get 0.00431 joules approximately. Okay, so that's just the change, right? I just said from the top to the bottom it's delta y. And we will talk about this other parts next class, but that's the basics. Now I'd like to introduce the concept of the total mechanical energy of this system. So when I raise a block up, or when a block is in the air, it has two types of energy. It has its kinetic energy, so depending on how fast it's moving, it has a certain amount of kinetic energy, and it also has energy stored between it and the Earth. This potential energy. We've only learned about gravitational potential energy, but we'll learn about other types later on. So the total energy is just going to be, or we also call it the mechanical energy, but I'll usually just label it E. It's the kinetic energy plus the potential energy. And the work done by conservative forces, all it does is it increases the kinetic energy and decreases U, or any changes in potential energy. Remember, work done is equal to change in kinetic energy? Well, we also define work to be the minus in the change in potential energy. So any changes to the potential energy result in the opposite change in the kinetic energy. And so if I were to rewrite delta K as K final minus K initial, and I were to write delta U minus delta U as minus U final minus U initial, I can rewrite things like this, such that it's the total energy at one point is going to be equal to the total energy at another point. So in other words, if there's only conservative forces, the total energy of the system stays constant at every point. Here it is formally, in an isolated system where only conservative forces cause energy changes, the kinetic energy and potential energy can change, but their mechanical energy of the system cannot change. So as long as there's not friction, as long as it's just gravity and some of the other forces we'll see, the total energy of the system stays constant. Here's a great example. I showed you some of this before of the different types of energy. So if I place this skater here on the track and I let her go, the bar chart on the left shows her kinetic energy and her potential energy as a function of time. I've removed all friction, so energy is conserved. If you look, the total energy bar stays constant. And so you'll notice that when she's at the very top, right when she stops, the kinetic energy is 0 and the potential energy is at its maximum because it's at the highest possible value. And when she's at the bottom, that's when she's moving the fastest. And that's when the kinetic energy is the highest, and that's when the potential energy will be the lowest. Right? So this sort of gives you an idea of how potential energy and kinetic energy are sort of interchangeable. And we can use conservation of energy to understand and calculate her speed and her heights and different things like that. If I add some friction, she would lose energy. The mechanical energy, which is kinetic plus potential, would go down, and she would lose energy over time. So I'd like to do sort of a simple example of that. So let's have here our potato. Wow. We have here our apple, and it has a mass of 0.500 kilograms. And it is a height here above the ground, y1, of 12 meters. And it's initially at rest. Okay, so if I have the apple there and it's at rest and I let it go, what's going to happen to that apple? Well, I guess I'm adding a second apple. What's going to happen to that apple? Well, it's going to start to move down, right? It's going to move down and get a little bit smaller. All right, we'll deal with that. So it's going to start to move down. When it's halfway down, what's happened? Well, when it's halfway down, it started moving, right? So it has some, we're going to call this V1, but it's initially at rest, but V2, when it's halfway down, in other words, when it's at a height here of 6 meters, it's sped up a little bit. And we can use conservation of energy to find how fast it's going. And the way I like to solve these kind of problems is I write down everything I know at the beginning. I calculate all the energies I know at the beginning. I calculate all the energies I know at the end, and I set them equal to each other. So let's do the calculation then. So what is the kinetic energy at point 1? So this is point 1, and this is point 2. So initially, it's at rest, right? So it's just 1/2 m0 squared. So the kinetic energy at point 1 is 0 because it's not moving. What is the potential energy at the beginning, or gravitational potential energy at the beginning? All right, so the gravitational potential energy at the beginning is mg times y1. Right, so let's calculate the initial potential energy at the beginning. So it's a mass of 0.5 kilograms times 9.8 times 12. So the initial potential energy is 58.8 joules. Right? And how about at point 2 when it's halfway down? So at point 2 when it's halfway down, the kinetic energy is going to be 1/2 mv2 squared, and that's what we don't know, right? And the gravitational potential energy at point 2 is going to be mg y2, which we can calculate real quick. It's just going to be, if you plug it in, it's just going to be half of that, so it's 29.4 joules. So we have the initial kinetic energy, the initial potential energy. We have the final kinetic energy and the final potential energy, but our only unknown is this. So we can use conservation of energy to find the speed when it's at the halfway point. And so conservation of energy basically is this. Conservation of energy. Conservation of energy. So basically the short version is that E at 1 is equal to E at 2. The energy at the beginning is equal to the energy at a later point, or kinetic energy 1 plus potential energy 1 is equal to kinetic energy 2 plus potential energy at 2. And of course, that's gravitational potential energy. I won't always put the G when it's only that one, but gravitational potential energy. And which of these is 0? Well, it starts at rest, so that's 0. So now we have UG2 here. Let me put in for UG2 is that's 1, sorry. MGY1 is equal to 1/2 MV2 squared plus MGY2. I'm going to move the Y2 over, so we have MGY1 minus Y2 is equal to 1/2 MV2 squared. I'm going to divide both sides by, or I can just cancel m on both sides, multiply both sides by 2, take the square root, and I get that V2 is equal to the square root of 2g y1 minus y2. So I can calculate that very easily if I learn how to use my own software. There it is. So 2 times 9.8 times 12 minus 6, so it's 6. It's 117.6, and I take the square root of that, and I get my final answer is approximately 10.8 meters per second. So that's how fast, if I drop that apple, that's how fast it's going once it's dropped halfway down. It's now moving at 10.8 meters per second. That's a basic application of conservation of energy, and we will be doing a bunch more of that in the next few days. Another thing that I can do with that is I can do something like there you go. If I throw an elephant, so here's an elephant on the ground, and I throw it upwards. Wait, can I arrange? No. Here we go. So if I have an elephant on the ground, and this is at point 1, and I throw it upwards with an initial speed of, I don't know, 5 meters per second. I'm very strong, so I can throw elephants very easily. And it's initially on the ground, so y1 is 0. Then I want to know, oh, and I guess I need a mass for this thing. So let's give it, I don't know how big elephants are. Let's give it 1,000 kilograms. Right? It's a baby elephant maybe. So I throw that elephant upwards. And I want to know, how high does it go? How high does it go? That's a good question. Now, here's the trick. It's similar to what we did before when we were doing this with kinematics, right? If I want to know how high it goes, that means when it reaches its maximum height, that's when it stops moving upwards. So that's when its velocity at its maximum is 0. So I know everything except y2. So I can solve this. So this is at point 2, right? So I know everything except y2. So I can say E1 equals E2, or K1 plus potential energy 1 equals K2 plus potential energy 2. Right? So kinetic energy 1 is 1/2 mv1 squared plus mg, and y1 is 0 because it starts on the ground, right? So that's going to be 0, equals 1/2 mv2 squared plus mg y2. And v2 squared is 0, so that's also going to be 0. So that simplifies things a little bit. 1/2 mv1 squared equals mg y2. Solve for y. So y2, you notice that the m's cancel. Oh, oops. Sorry about that. The m's cancel away. And so we end up with y2 is equal to 2 v1 squared over g. And so I can calculate that. And if we look at our numbers, right, it's 2 times, and what was the initial speed? It was 5 meters per second squared. So it's 5 meters per second all squared divided by 9.8 meters per second squared. You notice that on the top I have meters squared per second squared divided by meters per second squared, so I'm going to be left with meters. So what is my answer here? Well, let's do a quick calculation. So if I do 2 times 5 squared divided by 9.8, I end up with about 5.1. So let me write that down. So that's about 5.10 meters. So that's how high I threw my elephant. Yes. Okay. Ooh.